over rho, okay? When both end is fixed, then instead of a straight line, only certain points are allowed. So we do have forbidden energies. Energies. Forbidden energies. Energy is going to be h bar omega n. Something like this, right? That's what we have seen last time. Now, how can we use this in a real system? The first application is going to be the particle in a box. Particle in a box. Let's suppose we have a free electrons confined in a one-dimensional box by Coulombic force, whatever. Okay. So the dimension of the box, one-dimensional dimension, is going to be A, and the particle is sitting right inside this line. Okay. Then, since both end is fixed, we do have a confinement conditions or quantization, okay, quantization condition. Obviously, is going to be the A should be corresponding to the half wavelength to the multiple integer multiples. It should be something like this, okay? So the energy, if it is a free electrons, in other words, we do not think about the potentials. We just think about the kinetic energies that only. Then that is a momentum over 2m, and that is h square over 2m lambda square. Okay, because the momentum is h over lambda, right? And we know the lambda is going to be 4a n lambda square over 1 over lambda square. We put this lambda of this confinement conditions, insert to this, then we end up with lambda is some this values. Then we put that thing to the energy. Then now energy is going to be h square over 8m a square over half. All right. So since this n is going to be 1, 2, 3 integers, not the fractions. Okay. So the energy is not continuous at all. If you look into these energies, in other words, the free electrons in a box, free electron in a system, in an atomic system, then the electrons cannot have energies in between n is equal to 1 and 2. So if you plot this, then you're going to have something like this is ground, n equal to 0, for example. Then n is equal to 1 here. Let me put something like this. N equal to 1, n equal to 2, n equal to 3, n equal to 4. So as the energy state is excited to the high energies, the forwarding energy gap becomes large and large. Okay? That is the characteristic of free electrons in a box, in a solid atom. By the way, we have a knowledge of this in a sense that this is a solid, dimension A, and then, in a solid, the number of electrons, number of atoms is about 5 times 10 to the 22 atoms per cube. That is a typical number. Of course, it is different from atom to atom, but typically it's around this. In 1 cube, we have 5 times 10 to the 22. So, like a lithium, okay, and then potassium, alkali metals, all they have is the free electrons corresponding to the atom, 1 to 1. So we can think that if the solid is a lithium, we may think that we are going to have 5 times 10 to the 22 free electrons per cube, exact the same number to the atoms. Now those electrons, those number of electrons is confined in a solid, is not going to escape to outside of the solid. Then that free electrons will have a quantized energies. That the free electrons cannot have the energies in between this digit, okay, between this integers. That is an amazing thing. So, in other words, when the electron in the ground state is excited to the high energies, but somehow by applying electric field, typically, then we cut down the electric field, then the electrons which has been excited to up this n equal to 4, for example, then it should go down to the n equal to 3, and then this much energy has to be exerted to go out, and that is the X-ray. Okay? So if the n value is large, like 100 or something like that, then energy state and energy gap between n equal to 100 and 101, for example, is going to be tremendous. The delta E is going to be very, very, very big. So it has to emit the X-rays in that case. That is what happens when you have a copper, you apply the electric field, and excite the surface electrons to the high energy levels, and then those electrons, when they turning back, they'll emit the X-rays. That's what we use in the X-ray machine. Now, but in other cases where the simple harmonic oscillator, let's suppose we have a system that the materials, mass M, is going to be hanging by the spring like this, okay? And then it oscillates in between x naught, and this is 0, so that the total length is going to be 2x naught. Then we want to find out what is the energy state of this oscillator, okay? Then here in this case, 2x naught is the confinement or quantization condition. It should be. That is going to corresponding to the digital number, right? That should be corresponding to something like this. And we know the kinetic energy here, kinetic energy at x equal to 0, and the potential energy at x equal to x naught should be the same and the maximum. at each position. So we utilizing this fact, and then we have the energies to Gx naught 0. That is the spring force, right? Related energies. And then that is omega square m x naught square. And here the omega is a natural frequencies, which is corresponding to the gravity and the mass m. And x naught 0 is equal to m omega square, something like this. All right? And then the kinetic energy at x equal to 0 now becomes h square over 2m square lambda, and then that is n square h square 32m x naught square. And we have a quantization conditions, which is this. So we put that thing into this equation. Then the energy now becomes h square over 2m lambda square, and then n square h square over 32m, 1/2 1/2 omega square m energy, one reciprocal of energy, and then that is going to be arranged like 1/64 h square omega square 1/w. W is the same W here. Okay, then we rearrange that, and then we end up with the omega square, the W square. W square is going to be 1/64 n h square n square omega square, so that W is 1/8 n h omega. All right? It's amazing. So the quantized energy now it's going to be n over 2 pi over 8 h bar omega, h omega. Okay? This is the same thing to the n 2 pi over 8 h bar omega. Is it h bar omega? Yeah, h bar omega. And then here, the n should be 1, 2, 3, 4, something like this. This is a integer. So if you plot this, then now in that case, this is a n equal to 0, then n equal to 1, n equal to 2, n equal to 3, and delta E, the energy gap in between excited states, is all the same. There's a multiple of h bar omega. Okay? So no matter how high it is excited, then there is always nearby available energy state. So that in this case, in oscillator case, if you excite it to a very high energy state, then it just drop down to the next one, and then next one, and then next one, like this. So at one time, large emission of like X-rays, it cannot happen in this case. Okay? Even if you have a very high excited states, excite the oscillators to high energy levels. That means, okay, that means this oscillator, when you look at the solids, the atoms are connected with the springs, something like this, right? And then it is connected with the springs. That is actually Coulombic force, as a matter of fact. And then these atoms are going to be oscillate in the 3 dimensions, x and y and z axis, something like this, right? So this oscillator means it's atoms in a lattice. In a lattice. It's just like this. So this is the reason why furnace cannot emit X-rays. Even at elevated temperature. This is the answer. The simple string analogy can give you the proper answer to this very, very serious question. Why the copper metals, when we apply the electric field to the copper metals, how can those copper metal emit X-rays? On the other hand, why the furnaces, even at elevated temperature, it cannot emit X-rays at all? The reason is when it is electrons are confined, atoms are confined in a system, then it should be quantized, and the free electrons is like a particle in a box. It is quantized in this fashion. On the other hand, the lattice atoms is going to be quantized in this, where is it? The integral multiple of the h bar omega, okay, just like this. So that's why the furnaces cannot emit in X-rays. This is amazing. This is why we have to stick to the wave picture instead of a particle picture. If you think about the particles, if you think the electrons and atoms is just a particle, then you cannot explain this kind of phenomenon. Okay? Now, in the textbook, it covers the longitudinal wave in a rod, and you just read it, and you can just follow what you have developed for the string. It's just a simple theory. The only thing you have to notice is that in the longitudinal wave, the velocity, okay, the velocity is going to be related to the Young's modulus and the density, something like this. Okay. What happens in a transverse wave in a string? The velocity is related to the tension and the densities, like this. But in a longitudinal wave, where like a sound, okay, sound, it is related to the Young's modulus, and Young's modulus is what? It is the hardness of the material, right? So when you have a railroad, the rails, the sound can propagate very long way because the steel has a very high Young's modulus. Well, that's that. And then at the end of this chapter 2, this it covers the string, light, lattice wave, and electron wave that we are going to cover in the next 2 or 3 chapters has been summarized first. And we are going to discuss about this, so don't be nervous on this table. It's just equations that we are going to discuss. So that is the wave systems that we are going to talk. The first thing that we have to discuss is about the lattice wave. Lattice wave, as you may see, lattice wave means the atoms vibration in a solid. Okay, and then if you describe the energies the atoms can have in a solid, then we can say that is a kind of a wave with the energy is h bar omega, okay? Then we call that is a lattice wave. So physically, what you want to see is that when the solid, let's just think about the one-dimensional solid, okay? You can extend the idea to the 3 dimensions. Let's suppose we have atoms like this. It has a arrangement of atoms in a single crystal, for example. Then those atoms, nearest neighbors, are connected with the Coulombic force, attraction and then repulsion. And then within a balance, we call it the lattice distance, R0, right? If you apply the energy to this solid, then these atoms are going to vibrate somehow. So depending on the energies, how big the energy is, the atom's movement accordingly change, right? So with some energies, let's suppose we have some energies, and this is the end of the solid. Then this atom and this atom should not move at all. And then this atom is going to move to one direction. So we just think about the one dimensions, okay? Move one direction, then this movement is going to affect the next one, okay? And then this one is going to affect the next one. And then this one is going to affect the next one, and then something like this, okay? So the next one is going to affect the next one. Okay, something like this. I just want to explain what is the lattice wave is about. Okay? So with some energies to this system, the atomic arrangement at absolute